Yeah, I think last time we looked at differentiating power of x. That is, we had a function f, which is x power n, and we use binomial theorem to find the derivative of this f prime. That's the derivative. One way of writing that is n x to the power of n minus 1, right? Now, before we proceed and look at other functions like trigonometric functions or exponential functions, we can look at composition of functions. Then it makes life simpler to derive other functions. At the end of this period, basically, you should be able to derive, that is, differentiate any kind of functions which people give you, which are differentiable, of course, which are continuous and differentiable. Now, what is this composition? Supposing I have two functions, call them f and g, both are functions of x. That means they are continuous in a specified interval, which is part of their domain. That means we are now looking at a common interval. That means common to both. So in that interval, both of these functions are continuous in the closed interval, differentiable in the open interval. You can give a name to the interval if you want, a comma b is the range of values of x. A and b can be positive or negative, doesn't matter. Now we would like to find out whether we can differentiate f plus g as one example, f minus g, the difference, then the quotient, f divided by g. F plus g, f minus g are practically same, so we can merge the two as f plus r minus g. That's okay. Then we have f star g, that is, we multiply. Then we have a quotient. One last type is known as a function of a function. This, let me talk about that a little later. And we would like to see if we can differentiate or we can find derivatives of these. Once you say I've got a derivative for fx which is defined and derivative for gx at the same point which is defined, which means the appropriate limits exist. If you use the delta format for representation of that limit, life becomes very simpler. You can also use any other format of differentiation. For example, we have a limit of delta f, that means a small incremental change in f corresponding to a small increment change in x, delta f by delta x, as the delta x is made to tend to go to 0. This limit exists because they have said it is differentiable and that is f prime at that value. Similarly, we have one more limit which has been given as exists, limit delta x tending to 0 of delta g by delta x. Both are available. Now we need to find out whether we can apply the rule for these combinations. We can start with this f plus or minus g. How do you find this? This would be the limit, if it exists, of delta x going to 0 of delta of f plus g. No? How do you write that? F plus delta x, when you change x with an incremental value delta x, we get a new value for f, which is f plus delta x. Similarly, we get a new value for g, which is gx plus delta x. Minus old values, which is minus f plus g. The whole thing we have to divide by delta x and check if the limit exists. I think it's just a question of rearranging these terms. Correct. F and f will get cancelled. F plus, I should have written delta F here. G plus delta G. I think I made a mistake here. Doesn't matter, this is common. In fact, I'll tell you one small story about one of the brilliant mathematicians of the modern times, Srinivas Ramanujan. And he was from a poor family, not like an entitled family like C.V. Raman and Subramanian Chandrasekhar. They were all very entitled. They had contacts with the highest levels of British government when the British occupied India. Whereas Ramanujan was a poor fellow, and his interest was only in mathematics in life actually. He never wanted to do anything else, so he failed most of his exams. He never passed anything serious. And he used to sit down and he was interested in theory of numbers. Obviously, to sit down and write on a piece of paper is expensive, because paper is expensive. You know, one sheet of paper costs so much money. He could not afford it. So he used to do most of his calculations on a slate with a piece of chalk and rub it out, and only take the final results and write on that sheet of paper. You know, so in fact, most of his proofs are so concise because of that. You know, so this rubbing out is all right, I think I'm saying. Anyway, now it's just a question of rearranging this term. You can write that saying this will be limit delta x goes to 0 of delta f plus delta g minus, sorry, there's no minus there. This is cancelled there, divided by delta x. Or I can split this as two different fractions. Delta f by delta x plus delta g by delta x. We know that limit of a sum is sum of the limits, and that gives you the actual differential as f prime plus g prime. If you want for f minus, I think just that minus sign, you will get the same result, f prime minus g prime. That is not a problem. F star g and f by g might give you a little bit of trouble, so we'll look at that. So I've got a f star g. If I want to derive f star g, write that as a limit delta x goes to 0. F increases by an amount delta f, g increases by an amount delta g, and the product increases by an amount minus fg. Whole thing divided by delta x. We just have to expand this two linear functions we have. If, the fg and fg will get cancelled, of course. So I got f delta g by delta x, g delta f by delta x. So I start with g delta f by delta x plus f delta g by delta x. We have one more term, which is delta f delta g by delta x. Now I got a sum of three different terms. Limit of three terms is adding the three limits. It is straightforward. This would be gf prime at the first term. Second term will be fg prime. Third term is delta f actually going to 0 and multiply by g prime, so it will be 0. You don't have to write it. So this is going to be the answer for the product. So gf prime plus fg prime. That means when you have a product of two functions, derive them independently and multiply and add the two terms that you get. Simple. Sounds quite simple. Now we can look at f divided by g. So we need to look at limit delta x goes to 0. F plus delta f divided by g plus delta g. This is the incremented value of the quotient. I have incremented the individual numerator denominator minus f divided original quotient by g. So this would be the limit that we want to find. We can take LCM. So we have g multiplied by g plus delta g. So this will be gf plus g delta f minus fg plus f delta g. I think that gf will get cancelled, so let me not even bother writing it. So we have a g multiplied by delta f minus f multiplied by delta g. And the limit of the whole thing as delta x goes to 0. Simple enough. Now we take the individual terms and then write down the answer. When delta x goes to 0, delta f and delta g both tend to 0, so denominator is going to become g square. So no problem. So I would get g f prime. The first term will be delta f by delta x. We missed the delta x, I think. There is a delta x, the denominator. So delta f by delta x gives me f prime minus fg prime. Gf prime minus fg prime divided by g squared would be the derivative of the quotient. I think if we look at some actual examples, you might appreciate that. Let's just look at some simple examples where we know the answer beforehand, but we can derive it using these combinations. We have discovered the derivative of x power n already. What you could perhaps do is write that as a product of two functions. So I got an f, which is x power n only, but I can write that as x multiplied by x power n minus 1. So I got two functions now, one is x power n minus 1. So that I can apply the product rule for it, would be fg prime plus gf prime. So that means fg prime. So first function multiplied by the derivative of the second function, which would be n minus 1 x to the power of n minus 2 plus second function multiplied by the derivative of the first function, x power n minus 1 multiplied by 1. So we can take n minus 2 as a common factor. X power n minus 2 would be nx minus x plus x. This is x power n minus 1, one extra power, so plus x. No.
G of prime is prime values.
I got f g prime.
That's correct. Then the G of prime is.
G f prime. This is correct. So x power n minus 2 if I take out, what I am going to have is nx minus x. And here I will have plus x. So it will be nx power n minus 1, which is not. Oh, it's correct. Answer is correct. That's what I want. Anyway, that's what we should really look at is some new type of functions, or we can look at a polynomial itself. We have not seen the polynomial. Polynomial starts off with a, bx, cx square and so on. So we have a constant multiplied by a power of x, right? So we can think of that as a first extension of this. So let us say I've got one f, which is a multiplied by x power n. So a is a constant. I can do a binomial expansion and find the result, but I can apply the product rule also. A is one function which is actually a constant function whose derivative is 0 because it never changes, it will be 0. So therefore, f prime would be derivative of the first function multiplied by the second function, which is x power n itself, which is 0, plus first function multiplied by derivative of the second function, a n to the power of x minus 1. Simple. So a n x to the power of n minus 1. That would be the derivative. We can take a simpler, another example like I've got f, which is ax squared. Now is a combination of a couple of those rules that we have done, bx plus c. So I got a sum of three functions, so we have to derive individual and add them. Each itself is a power of n with multiplied by a constant, so we know how to do that, multiply a constant by the derivative. So this would be 2ax plus b, c is 0. Simple example. I'll take one last polynomial before we go to the next topic. F is 1 plus x plus x squared by 2 factorial plus x cubed by 3 factorial plus etc. I'll write one general term here, x power n by n factorial plus etc. till infinity. We have seen this exponential function, infinite series, and I want to derive that. I want to find out what is the differential of this particular function. I got it, sum of so many terms, we derive individual terms and add. So what is df by dx? In fact, this f is really, I can write that as e power x. E power x is this sum. So what is d by dx of e power x? First is a constant, 1 is a constant, so it is 0, nothing. X, when you derive, you get 1 plus x squared is 2x. So 2x by 2 factorial plus 3x squared by 3 factorial plus general term will be nx to the power of n minus 1 by n factorial plus till infinity. Now we can simplify this. We can cancel the constant in the numerator gets cancelled with the last part of that factorial. So 3 factorial, if you cancel 3 from there, you will be left with 2 factorial. N factorial, if you cancel the last factor n, you will be left with n minus 1 factorial. So you will get 1 plus x squared by 2 factorial plus x cubed by 3 factorial. General term would be x power, I can write n minus 1, I can write the next term also, x power n by n factorial plus etc. Actually the same as the original exponential series, which means this is also e power x. So now e power x is a wonderful exponential function because its derivative is itself, So I don't know how you can visualize that, which also means this derivative e power x is a continuous function. It is differentiable. It has got all the properties that we originally thought e power x was supposed to have. It's the same e power x. Actually, it's the same. So I can derive that once again. I can differentiate this e power x. That will be second order derivative of e power x, which is also e power x. I can differentiate that once again and once again and once again up to infinity. Infinity order. It doesn't matter how many times you differentiate e power x, you'll be left with e power x only. All the derivatives are the same, and at x equal to 0, which is e power 0, is 1. E power 0 is 1, right? So E is that wonder number where at that point, if you look at the graph of e power x, where the x-axis and on y-axis we'll plot the value of e power x. So at 0, when x equal to 0 at the origin, e power x is 1, which is e power 0, and it increases exponentially when you increase the x, and negative powers decrease exponentially, so it goes to 0. It's asymptotic. Now at this point, all its derivatives like speed, acceleration, jerk, snap, rattle and pop, whatever order in further orders, every differential is the same value, which is 1 only. So that's how it is increasing dramatically like that. Each contributes to the new value of e power x. That is one aspect. Now next, so now you looked at polynomials, which finishes one set of functions which need to be derived, that is differentiated, and exponential function we added. Now you can multiply a function with another exponential function. Simple example, like supposing I have got a function g of x, which is some function of f, some function of x called f, doesn't matter what it is, can be x squared, can be sin x, cos x, whatever you name it, multiplied by e power x. So you got a product there, and when you differentiate this, g prime would be same. When you have two functions, f prime g plus gf prime. So that means in that case it will be fx multiplied by derivative of e power x, which is e power x itself, plus derivative of fx, which is f prime x multiplied by e power x. So, which is really speaking is e power x multiplied by f plus f prime, or fx plus f prime x. Simple end result. So now we can combine these into any kinds of complicated functions and find their derivative, except that we have not looked at trigonometric functions. So let us look at trigonometric functions. Once you derive two fundamental trigonometric functions, jiva and koti jiva, sine and cosine, now the rest of the functions immediately follow, because you can always express the rest of the trigonometric functions as combinatorial functions of sine and cos. Secant is 1 over cos, cosecant is 1 over sine, tan is sine over cos, cot is cos over sine. So, other 4 functions. So, we need to look at sin x and cos x. Supposing I have f is equal to sin x. How do you differentiate this? Our standard practice is to write the limit. So, want to write that as a limit. Delta x goes to 0. So, we give a small increment to x and see what happens to sin x. Sin x is going to become sin of x plus delta x. Original value of sin x was minus sin x. So, this is the increment that sin x gets divided by delta x. Standard way of writing the derivative. If this limit exists, then sin x is differentiable at the point x. So, we have seen sin a plus b, we have seen that one of the reasons we did that sin a cos b plus cos a sin b. So, we write that expansion. So, we have a limit delta x goes to 0 would be sin x cos delta x plus cos x sin delta x minus sin x. That is the term which was left. Whole thing has to be divided by delta x. Now we have to rearrange these terms in a way that we understand, right? Sin x causes delta x minus sin x, you can take a common factor. So this would be sin x multiplied by cos delta x minus 1. I divide that by delta x plus, I just split the limits. I got 2 terms here. Limit of a total of 2 terms is total of the 2 limits. So plus limit delta x tends to 0 of cos x multiplied by sin delta x by delta x. This is the other term. Now we spent some time on these 2 special limits, if you recall. Sin theta by theta as theta goes to 0 is 1. We have seen that one limit. 1 minus cos theta divided by theta goes to 0 as theta goes to 0. I got not 1 minus cos delta x, I have cos delta x minus 1 is a negative of that. If this goes to 0, 1 minus cos delta x goes to 0, cos delta x minus 1 also will go to 0 from the other side. So, that is also 0. So, this is 0 and this is 1. So, you can write that. So, this limit is going to become 1 and this limit is going to become 0. So, the answer would be, so the sin x multiplied by 0, I can ignore the term, cos x multiplied by 1. So, derivative of sin x is cos x. So, it's a wonderful result that we got. We'll see how we can make use of this. Simple, straightforward. Now we can look at deriving cos x. That is the next step. Obviously, we require the formula for cos a plus b. We know that cos a plus b is cos a cos b minus sin a sin b. So that we know that. So we can write that. So supposing I have f is equal to cos x. I can write that right here. So what would be? So I got a f which is now the cos x. You can ignore the sin part of it. So what is df by dx would be equal to f prime limit delta x goes to 0 of cos f plus delta x minus cos x. So that would be cos x cos delta x minus sin x sin delta x. Cos a cos b minus sin a sin b. So this is cos x plus delta x minus cos x. Whole thing has to be divided by delta x. I skipped a step like Ramanujan. I don't have space on the board. No, like he didn't have paper. Doesn't matter. Equals. No, again, as usual, we have to combine these terms. So I got a cos x, cos delta x minus cos x. You can combine that as one word, one limit, which is cos x multiplied by cos delta x minus 1 divided by delta x. I'll divide that. Individually I'll divide that. Minus sin x multiplied by sin delta x by delta x. So we got our two favorite limits here. Sin delta x by delta x. I should have written limit there, but it doesn't matter. So this tends to 1, no question. Cos delta x minus 1 by delta x tends to 0. You've seen that? So obviously the result of this would be minus sin x. So when you derive sin x, you get cos x. When you derive cos x, you get a minus sin x. You derive that again, you will get a minus cos x. Derive that again, you will get sin x. Derive that again, you will get a cos x. Derive that again, you will get a minus sin x. Derive that again. That means you can do infinite number of derivations. It will keep going sin x, cos x, minus sin x, minus, plus, minus, sin x, cos x, sin x, cos x, sin x, cos x. It keeps repeating. And that gives us a fantastic opportunity to study those trigonometric functions in a special way. We'll see that later, first aspect. And that's why they are known as harmonic functions also, because they oscillate. Sin x and cos x, sin squared x plus cos squared x is always 1. That means they have a limit of minus 1, 2 plus 1. And the sum of their squares is always 1. That is the Pythagoras theorem. That is one other property of sin x and cos x. So they have these two fundamental properties of they're mutually each other's derivatives, one with positive sign, one with a negative sign. So initially you can see the parikramana or the walk around the circle. When you starting point, opposite side is 0, adjacent side is the radius. So that means sin 0 is a 0 and cos 0 is 1. So that is the starting point. And what happens is sin, if you look at the rate of increase, that is the derivative. No? So sin increases at the rate of the derivative. That is the rate of increase. Increases the rate of 1. That means the current value of whatever sin is there, that is the rate, it will start increasing at that rate. And cos, of course, what is the rate of increase of cos? Is minus sin. So it starts reducing actually. So cos will start reducing because that is a negative sign. So when you move from here till the right angle, what we call 90 degrees, from here to here. So if you drop a perpendicular, you'll find the altitude is sine or sinus, and the distance from the center is cosine x. So the altitude keeps increasing and reaches the radius, becomes 1, and the cosinus keeps reducing and hits 0. So that's how it is. And it goes the other way around. And this continues, this will go negative and become 0 and so on. So, and once you finish one round, that means that is 2 pi. 2 pi is the distance that we travel. And continue again, it will be back with the same old values. That means sine of x plus 2 pi. Any angle which is x plus 2 pi plus x is the same as x. Actually, the position is the same as x, must be equal to sin x. Similarly, cos of x plus 2 pi is cos x. Let's say they are harmonic functions because they keep repeating, and the period is 2 pi. So 2 pi is the period. So they keep repeating. Very interesting properties of these two trigonometric functions. Most of the properties were actually discovered in first few centuries in India, but anyway, that's besides the point. Now we can go ahead and differentiate or derive the other trigonometric functions using the combination rules that we have already seen and applied. That should be straightforward. So we can start with the tan x. How do you derive tan x? What is tan prime x? Tan x is sin x divided by cos x. Opposite side by adjacent side, the slope actually. Now this is like f by g. F by g, we know it is g squared in the denominator, and gf prime minus fg prime. So what is gf prime? Cos x multiplied by derivative of sin x, which is cos x, minus fg prime. Sin x multiplied by derivative of cos x, which is minus sin x. So I have got so I have written f as tan x and f prime as this ratio here. This is cos squared x plus sin squared x, which is 1. No? So we know that. So this would be 1 over cos squared x. We can also write as secant squared x. So d by dx of tan x is secant squared x. Now we can look at d by dx of secant x. Secant x is defined as 1 over cos x, so d by dx of 1 over cos x. We can find this in two different ways. You can think of it as 1 cos x to the power minus 1, right? That is a function of a function. Function of a function, we didn't actually cover that ground, so I won't use that. So we got a fraction here, numerator and denominator. So this should be square of the denominator, which is cos squared x. So gf prime minus fg prime. So cos x multiplied by derivative of 1, which is 0, minus 1 multiplied by derivative of denominator, which is minus sin x. So this will be a positive value actually. Sin x by cos x is tan x. 1 over cos x is secant x. Secant x tan x or tan x secant x would be the derivative. Now, similarly, we can write d by dx of cosecant x. This is almost you can write by symmetry also. Is d by dx of 1 over sin x. Sin squared x in the denominator squared. Now, gf prime, which is 0, minus fg prime. Would be minus cot x cosecant x. Okay. Now I can derive d by dx of tan x as the inverse of that. Sorry, cot x as the inverse of tan x and so on. So I suggest you can do that on your own. Let me leave that as an exercise. One last aspect of that combinations of functions is what I said is a function of a function. That means if you say we got a function f or function g to start with, which is continuous and differentiable in a given interval. So if you look at the plot, so I got a g. That means for every value of x in that interval, we can call it a, b. Every point, every value of x, it's a point on this interval, I get a corresponding value of g, which is the height of that graph at that time. Now the value of g itself I can use as a value variable, and I have another function f. I can plot f versus g. That means something like, supposing f was a curve, I'll give a simple example of f, was something like a constant or something. So it's parallel to x-axis, so it's constant. So now I plot that same f not with respect to x-axis, with respect to g-axis. So we imagine a g itself as an axis. It's not a straight line. Whatever curve is there, with respect to that, if you plot f, what happens? Correct. So that means for each value of g, I got a value of f. So f is a function of g, where g is a function of x. How do you derive? How do you differentiate, or how do you find the derivative of f was the question, right? Very simple and straightforward. Derivative of f with respect to fx, that is delta f by delta x, limit as delta x goes to 0. If you look at the function f, I have written as f of g. F depends on g. Whenever you get a new value of g, you get a new value of f, correct, corresponding. It's a mapping from g value to f value. But here I have got delta f for delta x. There is no x mentioned here. When you change x, what happens here? Actually, nothing happens immediately. You got another function gx. Whenever x changes with delta x, this g changes with delta g, and because of that delta g, f will also change. So that is why we written that as delta f by delta x, even though there is no x mentioned anywhere here. This you can simply rewrite. Here this delta g is coming in between. What you could do is, and we know that when you say limit delta x tends to 0, it also means delta g also will tend to 0, delta f also will tend to 0. This tend to 0 means it's actually not 0. No? Reach 0, but don't tend to 0, but don't touch it. No? So we can always assume delta x is not 0. It can be any tiny quantity as small as you please. So I can multiply this by delta g by delta g. So without loss of generality, because both are tiny quantities, is 1. 1 is a fraction. We just have to rearrange these 4 factors here. I can write this as delta f by delta g. That means I have taken this delta g below delta f, multiplied by delta g by delta x. Same. I just interchange these two factors in the denominator, and it's a limit of two factors of a product, so it would be a product of limits. So delta f by delta g, when you say write delta x tends to 0 also means delta g also tends to 0, obviously. So delta f by delta g, as delta g tends to 0, is df by dg, not gx. Delta g by delta x, as delta x tends to 0, is dg by dx. So differentiate f with respect to g and multiply by differentiating g with respect to x. So that's a function of a function. We can look at a couple of small examples to prove that. Let us say I have a function f which is sine x squared. Sine something is a function, and that something itself is a function of x. No? So like this is something like g is x squared, and I can write f is equal to sine g and g equal to x squared. You can really means f is a sine of some variable g, where g is x squared. So we have to differentiate f with respect to g, multiply by differentiating g with respect to x. So what is f prime? Cos g multiplied by, so 2x cos g is x squared, 2x cos x squared. When you differentiate sin x squared with respect to x squared, so you get cos x squared, So multiplied by differentiation of x squared itself with respect to x. 2x cos x squared will be the result. Okay? Yeah, that is very nice. One last aspect is what is known as an image function. I would like to show that shortly. What is an image? I can define the image function now. We'll come back and differentiate it. Okay, what is an image of a function? If you look at a plot or graph of any function, any function f is a mapping. That means I got the entire real number set, infinite number of points. Maybe our domain is a subset of this. Within the real set, there is a subset, which is basically a interval or whatever, a set of intervals. It also will contain infinite number of points. And when you say f is a function, range is again a subset of the same reals. real number system. So that means it maps each point to a unique point which is also a real number. So this is a function, right? Now the question is, can I have the reverse mapping, or reverse of it? From this point, supposing given this point in the range, what is the value I got for f, can I get back the value of x? Is the reverse. One problem there you will find, I'll give you a simple example. Supposing y or f is x squared. Every value of x I can find a x squared, which is there. But x squared, supposing I got an x whose value is x squared, I got a minus x, another point, which maps onto the same x squared. No? Minus x whole squared is also x squared. So it maps to the same point. So when you do the reverse mapping, we got a multi-valued function. For the same point here, I got 2 points here, I can't map. I have to select one of them. So that is going to be a problem with this image. So this, what we call, is a square root function. Square root of x. Actually, there are 2 square roots of x, really, which is plus or minus. So, and square root of x also can be written as x to the power of 1 by 2. Another exponential format of writing. We assume that whatever rules we had for x power m, saying x power m multiplied by x power n is x power m plus n and so on. So whatever exponential exponent arithmetic that we are doing, we'll assume it is true for real numbers also, real exponents also. So I can write the same square root x as x to the power of 1 by 2. Cube root x will be x power 1 by 3 and so on. We can write that. Now x power 1 by 2, we can either treat that as a multi-valued function because it has got 2 square roots. Same way like square root, or I can write that as square root of x. 3 different ways I am writing the same thing. Square root of x and x to the power of 1 by 2. So the catch here, when you say I am taking square, so this first part, I can read that as I am taking square root of x. Correct? Then I will get 2 values. What are the 2 values? What we call root of x, that is the positive square root, and the negative will be minus square root. So plus or minus square root of x, and this will be plus or minus x power half. If I write it like that, advantage is, now when I write root x is not multi-valued, is single valued, is positive square root. X power half is positive square root. If you want a negative square root, you have to say minus x power half. So that's the advantage. So when you have this kind of functions, the reverse mapping, you have to make sure it is single valued. One other example could be, I have got one y is equal to e power x. Right. I want to do reverse mapping of that, which means actually what I want is x equal to e power y. Correct? Here, x equal to e power y looks like x is a function of y. No, I am still treating y as a function of x. And what is that value? What is the exponent value? Is actually designated as the logarithm. So that is the definition of logarithm. Logarithm again, there are different logarithms which are used. The problem, this is known as a natural logarithm because we use e as the base from which we have raised the power. There is one more logarithm written as log, which is logarithm to the base 10, which is log 10. Log is log 10, other one is ln. What is log 10? If I have x is equal to 10 power y, then y will be log to base 10 of x. Correct? So log or logarithm is the inverse or image function of e power x or even 10 power or any power, a power x. No? So ln is that function. So if you say now I have got y is equal to ln of x, can I derive that? Can I differentiate what is the derivative of ln x, that is log x. We write it as ln but read it as log only. So log 2 base e. Read it as log, write it as ln. I would have preferred to write this as log itself. I'll tell you the reason. About 30 years back or 40 years or 50 years back, these base 10 logarithms were really used in classrooms. We used to do calculations when you want to multiply big numbers or divide numbers, whatever. We were using logarithms, no? Logarithms to base 10. You know that. So there's a book also which gives the list of or table of logarithms. No? Now, unfortunately, today we don't use those tables called Napier's table. Known as Napier's. Napier is a person who, I think, prepared the first such set of tables. We don't use it because we got handheld calculators or even mobile devices which can do the computations so fast. We don't need these logarithmic tables. This is one which we are using, right? Another thing which we are using were called as slide rule for doing multiplication. It's also logarithmic way of multiplying. We were using that. So when you're going to engineering colleges, you have to carry that slide rule in your hand, you know. So we are doing that, or carry that book. So. And the calculators came in just towards the end of my education at that time, and late 70s. So at that time, the teacher didn't want you to use the calculators to find products. So they said calculators not allowed, but log tables and slide rule is allowed. And so on. Nowadays, nobody bothers. People are so used to these calculators, and even calculators, I don't think anybody uses. They just use the mobile itself has got a calculator function or whatever. I still remember Japan got used to this calculators as a general population than India, much faster. So I had a meeting at the time, they were already used to using calculators. No? So, right, persons of my age, my own age, they were already not using slide rule and not using these. And once they use that, the thing is, they don't like to memorize. You know? We used to always do it memorizing the multiplication table, for example. Now 1 to 10 or 1 to 20 is a standard practice. I still remember my father used to insist that I should be able to repeat the multiplication tables backwards from 20 onwards. 20 20s or 420 or 20 10s or 229, like that. So 180 and so on. So even recite it backwards so you never forget in your life. 1960s or 114, won't forget it. So in the meeting we are doing some quick, they were calculating some numbers, saying, so I get 5 cents for this, and I got 7 of those transistors or whatever resistors, and the total you have to pay for it is, I said 35 cents. That fellow, Japanese fellow, is actually taken out his calculator, saying 5 multiplied by 7. I said 35. You know. He said, what? You're doing that orally, mentally, like Shakuntala? I said, no, we are all used to this simple arithmetic like this. They can't even do this calculation mentally, no? I think they're mental people, if you ask me. At least memorization is not good, I know. But then, as part of our education, some things must be memorized. Like, for example, this multiplication table from 1 to 10, preferably 1 to 20. Okay. Then next, what I found really useful is some of these formulae that you find, like a plus b whole square or a plus b multiplied by a minus b. You have to memorize those. Or sin x cos x. So like d by dx of sin x cos x and minus sin x. Some of these things you must memorize. Otherwise, I know you can find information at your fingertips if you have your mobile. But then our thinking gets obstructed if you don't instantaneously recall those values. So memory is very good. So that is why probably today they could have written this as log x itself, because nobody uses log 10x anymore. No? But unfortunately, all the literatures, papers, maths paper, everything has been written as ln x, natural logarithms, and log x for Napier's 10-base logarithms. We can't do anything about that, so we stick to it. No? So something has been is being used for so long by so many people, billions of people, that we can't change it now. You can't change saying 1 hour has got 60 minutes. No, you can't suddenly change it to 100 minutes. France did attempt to do this meterization or metric, everything 100, 10, 100, 1000 and so on. So they have kilometer, kilogram, gram, everything multiples of 10. Unlike British had pounds and, you know. But then hour to 60 minutes, minutes to 60 seconds, you can't change because that people are used to it for so long, for 3000 years or more, that is impossible to change that. So they left it as it is. No? You can't change that. So now coming back here, so I am writing it as ln x, but please read that as log x. So what is log x? So what is the dy by dx? Now simple way is, how do we do that? We look at the limit. So now if you say what is dy by dx is a limit delta x tends to 0 of delta y by delta x. No questions on it. So obviously when delta x tends to 0, delta y also will tend to 0. I can also write that here. Delta y also is tending to 0. Correct. And both are non-zero. We don't say we touch 0. So delta x is non-zero, delta y is non-zero. So I can invert it. So I can write that as limit delta y goes to 0. No, I won't write delta x at all. I know even that is going to 0. 1 over delta x by delta y. Correct? Which is, so limit of a quotient is quotient of the limit. So top is 1 divided by, what is delta x by delta y? Limit as delta y goes to 0 is dx by dy. No? So dy by dx is same as 1 over dx by dy. So it's actually a ratio of infinitesimal change. Basically the ratio. Obviously we are dividing y increment from x increment will be 1 over dividing x increment by y increment. So obvious, it's very obvious from the limit. So if that is the case, so what we could do perhaps is we have y equal to ln x, which means really x is e power y, correct? That by definition of logarithms, so we differentiate this with respect to y now. So what is dx by dy is d by dy of e power y. The exponential function we have already found is e power y itself. Doesn't change. Any number of times you derive, e power x or e power y remains the same. So therefore, what is dy by dx is 1 over dx by dy. So which is 1 over e power y. I mean, I don't want the answer in y because y is not our variable. I want the answer in x. So substitute back x for y. What is e power y? 1 over x. So when you differentiate y equal to ln x, what you get is derivative is 1 over x. 1 over x is the derivative of log x. So the rate of change of ln x is actually 1 over x. Okay. So when x increases, ln x increases, log x increases, but the rate of increase is decreasing because of that 1 over x. Okay, that is fine. I would like to basically stop talking about this differentiation. So we'll go to the other part of the calculus. Remember, calculus is made of two parts. Differentiation on one part, integration on the other side. So we never looked at integration. In fact, what people wanted was integration. If you ask me what Newton wanted when he wanted to do planetary motion computations, what we want is integration, really speaking. But integration is a messy thing which you can't do, really speaking. So first you have to discover the differentiation, which is exactly the opposite of integration. And the purpose of differentiation is not differentiation, is actually integration, really speaking. So we'll see the connection between the two. So there is a fundamental theorem of calculus which connects the two, differentiation and integration, we can see. Before that, we have to look at integration itself. Integral itself as a topic. Now, integral, again, we have some problem. In history, we have had some problems. Basically, I think because of the rigorousness of mathematics now. As you realize, the rigor in mathematics was improved dramatically after they introduced some new terminology and new definitions. Set theory of George Cantor, Cauchy's infinite sequences, Bolzano's infinite number of nested intervals. All these they helped introduce rigor in mathematics. So as the rigor changed, obviously definition of these definitions also will change. Even differentiation definitions, we should take it as intuitively correct, but really speaking, you need a very rigorous way of handling that. But the answer is correct. In 99% of the cases that we are interested in, what we are doing is correct, so we'll go ahead. Integral, the same thing. So there are different definitions of the integral. And one of the popular modern definitions, if you can call it modern, was given by a gentleman named Riemann. So we talk of Riemann integrability, just like we talk of differentiability. That is, whether we can differentiate is known as differentiability of a function. So we need to talk of integrability, whether we can integrate a function also. What is that integrability definition itself? There are different definitions which different people have given. I would like to use this Riemann's definition of integrability. So what you basically get is a Riemann integral. I mean, actually you get an integral, but the definition is based on Riemann integrability. So we'll call it integral, but the method employed or technique employed in specifying is the Riemann's technique. Okay. Now, what is that Riemann integrability? We define that, and then we define what are called integrals. This is what we want. I want an integral which is exactly opposite to what we use as derivative. This is the fundamental theorem of calculus. Integral, there are two kinds of integrals. One is definite, is a known rational value, it's a definite integral. Other one is indefinite. Actually, the relation to derivative is for the indefinite integral. We start with defining the definite integral. So we employ the Riemann's integrability condition and say the function f(x) should satisfy that condition. Then we define the value of Riemann integral, which is actually definite integral. It's actually a definite integral. So we define an integral. Now, how do we define Riemann integrability? We are talking of a function f in an interval, obviously. So I got an interval maybe from A to B. You have to write that specifically. A to B is the interval. In this case, I have shown B as a bigger number than A. Both can be negative, both can be positive, doesn't matter. B is to the right of A. So I have written B greater than A. That is the picture. That's how it is. Or it could be to the left, the meaning will become different. So I got these 2 points in this interval. So interval is obviously the closed interval a comma b. Obviously our function f must be continuous. Over this closed interval. Otherwise there is no question of integrability. It must have a point, well-defined value for each one of the points in the closed interval. Right? Now, this interval itself, we are going to divide that into subintervals. N number of subintervals. Okay. So that means I am going to mark off points here as x1, x2, x3 and so on up to xn minus 1. I also have x0 which is same as a, and I also have xn which is same as b. So I got these points x0, x1, x2, x3, xn minus 1, xn, where x0 is same as a, xn is same as b, and all others are in between, and with a definite inequality. That let me write that inequality. The same, whatever we have shown geometrically, I can write algebraically, is a equal to x0, which must be less than or equal to x1, less than or equal to x2 and so on, less than or equal to xn, which is equal to b. I could have written less than. Instead of less than or equal to, you can write that as each as a less than. So you got ascending order of values, real value x0, x1 up to xn, where x0 is a and xn is b. Then, so you got the set of n. I've got n intervals here now. Correct. x1 to x0 is one interval. So how many intervals we have? We have n closed intervals. So I got one. x0 comma x1 is one interval. x1 comma x2 is another interval. And so on, all the way till x minus n minus 1 comma xn is the last interval. Correct? So I got n intervals here. Of course, the first value of the first interval is a, last value of the last interval is b. That is different. Now, we tag these intervals, tagging. Tagging is actually select one point in each of the intervals. I want to select one value in this closed interval, one value here, one value. Every interval we will select a value. Like for example, I will select the value, tag value as t1 in the first interval, t2 and so on up to tn. I got n intervals here. So I got these tag values, which is t1, t2, t3 up to tn. Now we can select anything as tag value. Okay. This tag value is a property of the function actually. Is a value of the function actually. So these are values of f. What value of f you will use for a given interval is up to you. I'll give you a simple example. I can always use the left side value as the value of the tag. That means fx0, fx1 up to fxn minus 1 can be the tag values. That's the least or minimum value. Not minimum value of minimum x, value of minimum x. Or fx1 I can use. Or I can look at the maximum value of f in this interval and say that is my tag value. Whatever. You can do that. No problems. Now the second assumption is these intervals are not necessarily equal size. I can have intervals may be different sizes also. So we specify what is known as a mesh. Mesh is a maximum width of an interval. Maximum value of xk minus xk minus 1. For a given value of k, xk minus 1 is the width of that interval, and I want a maximum value for k between 1 to n. This is known as a mesh actually. It's called mesh. Mesh is the maximum width of an interval out of these n intervals that we have. Now we define a partial sum, which is going to become the definite integral in the limit. It looks like we are doing a lot of new nomenclature we are introducing, but actually principle is very simple once you understand what I am talking about. So we define a partial sum, you can call it Sn, a sigma k equal to 1 to n. That means we are walking over these n intervals, and for each interval we multiplied the tagged value of the function or value of the function for the tag in the interval by width of the interval. Now, if you look at this graph, now you'll understand what we are trying to do is, we got these intervals. For each interval, we are selecting a value. Let's assume we just selected the function value of the first left side of the interval as the value. That means I want to draw a rectangle here and find the area. What we are trying to do is find the area under the curve, really speaking. So ftk is the height at A for the first rectangle. Xk minus x1 minus A, x1 minus x0 is the width. So that product is the area of this one slice or one rectangle. For the next one, we are multiplying x1 height at x1 multiplied by this. Again, we are multiplying this. Correct? No? Sometimes this rectangle goes above that curve, or sometimes it goes below the curve also. It's quite possible, so you'll find gaps of it. So this area is not actually equal to the area under the curve. So you can see what we are trying to find out is the integral actually defined this way, written this way also, is from A to B. You have to specify from where to where we are trying to find the area of fx dx. This is how we write the definite integral definition, right? We find the area. How do you find the area? Is to reduce the width of these slices indefinitely, so that those gaps they merge into the curve. No? So that's what we are trying to do. Correct? How do we write that? Is equal to limit mesh goes to 0 of Sn. Remember, Sn is a partial sum for one type of subintervals that we have created, which has a mesh. I want a mesh size to go to 0. When mesh size goes to 0, is the maximum width of one slice. Obviously, everything else goes to 0, and you get infinite number of those slices, and you will get the area correctly. So that is the definition of the definite integral of a function from A to B, which actually computes. What we are trying to do is to compute the area under this curve from A to B. That is what we are trying to compute. Okay? Now we'll see how we can use this effectively.